Okay, for section 8.3, we are going to cover hypothesis tests in even more detail. But first we want to recall what a p-value is from section 8.2. So as a reminder, the p-value is the probability that if the null hypothesis is true, that our test statistic, and so far we only know z, will be as extreme or more extreme than our observed value. Okay, so let's suppose we're performing a coin spinning experiment. If the coin is fair and we spin it, then the probability of it landing on heads should be 50%. So we're going to let our null hypothesis be that it is fair, that the probability of getting a heads would be 50%, and our alternate is going to be that it is not fair, or that we would get something other than 50%. Two different students performed the experiment with the following test statistics. Student 1 gets a z-value of 1.98 and student 2 gets a z-value of negative 2.02. Which of these test statistics has the smaller p-value and what does that mean? We're going to sketch the associated standard normal distributions. So I'm going to sketch one for student 1, a standard normal distribution, and another one for student 2. Okay, so standard normal means our center is at 0. The first student's z-value was 1.98, so that z-value is right here, let's say. But what's important to note again is this was a two-sided or a two-tailed. So when we find the z-value, it ends up on both sides. So this one back here as well. And again, what the z-value does is it says that the probability then is the area that is beyond that value. So what's back here in the tails. So that's what student 1's looks like. Student 2's very similar. Except their z-value was negative 2.02, so a little bit farther than the 2. And again, because it was two-sided, it means we have the other side as well. So here's what their curves look like with their z-values marked. So which one of these would have the smaller p-value and why? So we need to remember that the p-value is a probability, which is an area under the curve. So if it has the smaller p-value, it has the smaller area shaded under the curve. So which one of these two, I know my drawings are not that great, but which one of these two would have the smallest area shaded? Well, it would be this one, right? Because this one is, the z's are farther out, leaving less area in the tail. So student 2 has a smaller p. There, so basically what you want to kind of remember is that the z-values farther from 0 give smaller p-values. The farther away from 0 you get, then the less area there is to be shaded. Okay, so we want to talk about balancing mistakes. So recall that we usually set the significance level, that's alpha, we usually set alpha to 0.05. What this means is that there's a 5% chance that we reject the null hypothesis even though it's true. So we go through the whole process, we get to the end, based on our alpha value, we say, okay, we're going to reject. Even though you have done absolutely nothing wrong in your work, there's a very small chance, a 5% chance that you reject it even though it was true. And this is called error 1. It's the first type of error that could happen. So then the question arises, well, why don't we set this to 0? Why don't we make it a 0% chance that we ever would do this? And well, it's because what that would do is that would basically make another problem even worse. So the smaller we make this percentage, then the larger another percentage gets, which is the probability of doing the exact opposite, which is failing to reject the null even though it's wrong. That's your error 2. So error 1 is rejecting it when you shouldn't have, and error 2 is failing to reject it when you should have. So it says again to think of this as the jury analysis, and the null hypothesis is being innocence. The first type of mistake is the same thing as convicting an innocent person, and the second mistake is letting a guilty person go free. So clearly neither of these are a good thing, and you really can't lower one without raising the other in general. There's only one way to lower the probability of both types of mistakes, and that is to increase your sample size. That would improve the precision of your tests so that you make mistakes less often. But other than that, if you bump down the 0.05, if you make that a 0.04 or a 0.01, it would lower the likelihood of error 1, but it would raise the likelihood of error 2. So you kind of get nowhere doing that. Researchers call a result what we call statistically significant. When you reject the null hypothesis. So anytime you get to the end and you say, I found enough evidence to reject this null, that is called statistically significant. That means that the difference between the data estimated value and the null hypothesis value is so large that it cannot be convincingly explained by chance. It wasn't a fluke. However, you can get statistically significant results that are not necessarily meaningful. So there's another term called practically significant. Which is a result that's both statistically significant and meaningful. So here's a very easy to understand example of that. It says, what if there was a study that came out tomorrow, let's say, that showed a statistically significant result that talking on your cell phone every day will increase your chance of getting cancer from 1 in 10 million to 2 in 10 million? Would you stop talking on your phone immediately? I'm taking a guess out on a limb here, and I'm guessing for most of you it's probably not. For me, it's probably not. So this is not a practically significant result. It's statistically significant. There was enough data to show that this would not be due to just random chance, that there really is something going on, and that talking on your cell phone really would increase this chance. But it's not practical. That very, very small increase probably isn't going to make us change our daily habits. So you can see how statistically significant things happen all the time, and it's sort of in the eye of the beholder, from individual to individual or from group to group.